Functional block model. A functional block model is a type of model that has functions that are often represented as nodes or points or blocks, and these nodes, points, or blocks are separated by pathways which are directional. The metaphor that comes to mind with block models, actually there's several metaphors, but probably the most common one is one of having machinery in some sort of assembly floor or manufacturing floor, where you've got objects that are moving on assembly lines and operated upon by machines or people that do something. So the machines or the people then are acting as the functions, and the assembly lines are these directed paths where objects flow. Now, this is a kind of a discrete manufacturing style of metaphor. There's also the continuous metaphor. You can imagine that you've got a lot of pipes and you've got water, and the pipes carry water from one place to the next. Pipes can branch off. They can kind of branch off and fork, or they can join together once again. There can be valves and tanks and other kinds of things like this. So this is a kind of fluid metaphor that represents a continuum in the type of object or data that are flowing through the network. FBM, acronym for Functional Block Model. Again, a network of blocks involving directed data flow. Each block mathematically is represented as a function, or specified rather as a function, in the general sense of the word function. For instance, a lambda function, or a function that you might find in your favorite programming language. You'll note that if you think about it from the programming language standpoint, functions are a little bit different than procedures, because functions take input and produce output. They produce a result, as opposed to a pure procedure where there's a set of steps but not necessarily an end result. And finally, a block that's acting as a function may process data immediately, or it may actually queue the data. So these blocks can be quite sophisticated. Go ahead and draw a picture of a function. And the first thing is that a function can be presented in many different ways, but a common way to present it two-dimensionally is to use a rectangle. So we'll say that this is a function f, and that this function has got some inputs that we'll represent over here with arrows. Again, a very common two-dimensional presentation denoting flow. And some arrows right here, perhaps. These are inputs, and these are outputs. Now, normally the function has one output, and that's most common, but if the output itself is a tuple or a multidimensional thing, then you can represent it with multiple arrows or multiple outgoing arcs, which is why I've done so here. Now, you can also, if you want, you can have inputs to this function on one side like that, and then put in parameters over here, which really just serve as inputs again, but perhaps of a different sort. Perhaps the parameters are constant, whereas these inputs are varying into f. So f then takes inputs in the way of varying values over here, varying streams, takes constant streams here, and produces outputs. Okay, let's go ahead and represent an example FBM, or functional block model. What we're going to do is we're going to go ahead and put in 4 blocks like this. Okay, and we're going to make this first block a summation, which we'll designate as sigma. And we'll say that the first input we'll label U1 and the second one U2. Then this is U3 and this is U4. They're inputs to this second block over here. And this will be a times. So this sums its two inputs and this multiplies its two inputs. Then each one of these produces an output, which in turn goes into this block, which we'll call a divider, which you could call div, or you could just put a division sign. And then we'll take the output of that block and then wire it into this block, which we'll use an integrator, and we'll use the integration sign for that. And then the final output will be labeled y. So that represents the output from this. An important part of talking about functional block models is to note that these variables that you see, U1, U2, U3, U4, and Y, along with any other variables that we may wish to create to denote things on, say, this arc, and this arc, if we wanted to do so, that these variables are functions of time. So even though I've been a little bit lazy and I just say U1, in fact, if I'm going to be correct about it, I would say U1 of t. It's very important to note that because it's a signal, it's a time-varying signal that's coming into and flowing coming into this block and then flowing through this network. So every one of these variables is a function of time because we're in fact talking about signals flowing through the network, not just simple values that happen to be located within variables. Now let's go ahead and erase this, and then we're going to go over a second example of a functional block model. And in this second example, we're going to do a little bit of a simulation along with it. So this is going to be a 4-block model. And I'll just put the 4 blocks like this. And in these 2 blocks I'm going to put integrators. And then I'm going to kind of wire up the diagram or the model like so. Okay. This is going to be a constant block. A constant block we just say is a generator of constants, and we'll just say K for constant. Why not C? Well, we're just feeling a little ornery, so we'll use K. And then X, and this just will designate multiplication. Now we're going to label this a little bit too, so that we have some variables on here. Again, like in the previous diagram, every variable that I put on here is a function of time. We're going to put x double prime, which refers to the second derivative of x with respect to time. This is the first derivative, x prime, and there's the integrated variable x. And then we're going to put negative a here, where we pick a particular value for a. Okay. Now, one thing that's kind of interesting about this diagram is you can note that first, even though we haven't talked about equations in this module, that this network is equivalent to this equation. X double prime is equal to minus ax prime. Why is that the case? Well, if you take a look at this stuff up here, all you've really got is a way to represent 3 variables by putting 2 functions in between 2 of them, or the pair. So the relation between x double prime and x prime is an integral sign, and the same thing goes for x prime and x. And so if we go ahead, really what we've got is you've got x double prime equaling the output of this. And the output of that is nothing more than minus a times x prime. And that's exactly what we have right here in the equation. Now you might rightly question, well, if we can represent the equation like so, and we can represent the equation like this, which seems to be larger and more bulky, why would we want to do this versus that? And this gets into a fundamental issue of metaphors and modeling, and basically the question of why do we choose one model versus any other. Now in this particular example, often what happens is that a scientist or engineer will choose to use this as a model for a system as opposed to this when there is some spatial correlation between the elements, the visual elements in this model, and the physical elements that are being modeled. A simple example would be a electronic circuit, at least the old-fashioned kind, where you could get your hands and fingers around the discrete components and just lay them out on the breadboard. And you might find in that particular case that you need to wire up things just as you did here, and that those components had functions that mirrored those that are in this model. They had an integrator, electrical component, let's say, and a multiplier, and something that was a generator and generated constants. So this then would look like the thing being modeled, and that's its advantage. That's a metaphorical reason, which is for actually constructing the model like this, as opposed to removing all of that information and simply creating a balance, an equation of balance, which you see in this differential equation right here. Now what we're going to do now is we're going to reuse or use a numerical technique that's introduced in the equations module as the equational representation of a model. And we're going to go ahead and hand simulate this just very simply. First of all, we need to get some initial values here. For instance, a, we'll go ahead and make a equal to 1. So that means that what you have here is minus 1. Right, you got minus a, so I'm just going to put minus 1 there because that's just going to permanently come out of here. Likewise, we need initial conditions for what amount to x sub 0, which means x at time 0, and the first derivative of x with respect to time at time 0. We need values for these initial conditions. We're just going to make it very simple. We're going to make those equal to 1. So I'm going to put a 1 coming out here at the integration block and a 1 coming out here. So that's how you view initial values for functional block models that have integrator functional blocks, is that the output represents the initial condition attached to that block. Now, given this, we can actually start doing something, but we still need one more thing. To do numerical integration, we need a method, and we need some sort of integration delta time. So let's talk about the method first. And again, this method is described in more detail in the equations module, but we can use forward Euler's method, which is probably the simplest possible thing. And we would say that our value of x is going to be whatever it was before plus delta t, which we'll talk about in a second, okay, times x prime, or dx dt, whichever you prefer. So this is Euler's method, and it just basically says, hey, take what value you had for x, or more generally, what value you have coming out of any particular integrator block here, add delta t times whatever is going into that integrator block, and then that's your new value for x. So it's important to see this formula expressed up here. What I've really done is I've showed the relationship for this integrator block using x and x prime. But down here, there's no reason why you couldn't say take x and say, well, that's x prime and this is x double prime. Okay, Euler's method just says take the thing coming out, and the new value of the thing coming out is equal to the old value of the thing coming out of the integrator block plus delta t times the thing going into that block. And so that's how you do everything right here. So for instance, the new value coming out of this block would be what? It would be equal to whatever the old value is, 1. There's 1 right there. And then delta t is any value you want it to be. Generally, the smaller the better, so let's just make it 0.01. And we'll multiply 0.01 times the thing going into the block. Well, what's the thing going into the block? It's going to be 1 times -1, which is equal to -1. Right? So what we have right here is we've got 1 plus minus 0.01. Or 0.99. Okay. So 0.99 then is basically going to be equal to this right here. So we can go ahead and erase this because that's... Let's find the eraser. This is going to be 0.99. Now we have a choice. What we could do is we can integrate this block using this new value we've computed from this integrator, or we can use the old value that we had here. And these issues, along with numerous others, are part of the task of numerical algorithms and numerical integration in particular. And we're not going to be talking about them other than just to reference them. Our purpose is in modeling, which means finding the appropriate metaphor and presentation and representation and specification for the model. But this at least gives you a start into how you might hand simulate. I mean, the next thing you would have to do is you would need to calculate the next value of x. And then you have this feedback loop. And every differential equation is in fact a feedback loop like this. And then by going through this process, you end up calculating x, and hopefully x converges, or at the very least x produces some sort of graph over time, which you refer to as your solution curve. You come back to the definition momentarily and then move to an example of a functional block model. And this particular example is kind of general, but still deals with the area known as automatic control. In automatic control, we have the following elements, which we'll draw in a moment. We have a reference input, or a goal, a comparator, error, controller, actuator, power generator, a control process that used to be known as a plant and sometimes is in some control textbooks, and finally a transducer, which reads the output from the plant or the controlled process. So let's go ahead and draw a functional block model that is an example of automatic control, and as such it will be somewhat general. We're going to start here over on the left with what we'll call our reference input, or R sub t. Like the other differential equations we talked about, the other variables for functional block models, we always have time, or t, as a variable. Now we're kind of going to violate our two-dimensional icons here by using a circle, but this is quite common. This is a common symbol to use in control circuits for a thing called a comparator. So this is our reference, and this is our comparator. I'll just say comp for short. And then we're going to end up producing an error signal, and I'm just going to avoid putting t just because we know that t is going to be present, so we don't need to draw it every time. So I'm going to draw the whole thing just so that we can talk about how this works. So here I may have a controller or a compensator, which I'll say control. Here I have an actuator and a power amplifier. We might have some noise entering the system, And noise can be input in different places, but let's say that noise is introduced right here. And that's a secondary input, a stochastic disturbance. These little comparators then are going to have little signs, and these are weighted signs that are multiplied times the input that they have in the arc that's pointing to them. Now finally, this is the thing being controlled. This is the plant or controlled process. And it produces an output, which then is read by something we call a transducer. And I'll put trans right there. I'll bring this up here like this and feed this back into here. And my term, the verb that I use, feed, is important here because, in fact, this is an example of feedback. And so with respect to automatic control, you often hear the terms negative feedback or positive feedback. And this is an example of negative feedback because we're multiplying the resultant times a -1, which is designated as just a minus here. So this is the goal of the reference signal. We say, gee, how different is the goal from where the process or the plant actually is right now, the thing being controlled? How different is what we're trying to get to from what really it is in terms of position or orientation or whatever is the thing that we're measuring from the output of this process. Whatever that difference is the error. E for error. The error then drives the control system and then is fed back into the process. And the best way to go through this is to take an example of something that you know well, such as automobile, and just put some different words on here for the automobile. Let's say you're controlling an automobile. Well, the process or the plant or the thing being controlled is the car. So I'll put these in uppercase for the automobile example. So that's a car. That's the thing that is being controlled. You have a desired speed for the car, and this is really part of your cognition, or your central, which includes your central nervous system, or is driven by your central nervous system. So this is your desired speed for the car. We'll put in here desired speed. Then you have a foot accelerator pedal, so I'll say pedal for that element. We have an engine, which is the power amplifier. That's the thing that really just amplifies a signal that it receives. That's essentially what the engine does. It gets a signal and then essentially amplifies that to create movement. Then over here we have the speedometer. That's the thing that tells you how fast you're going. So let's go ahead and take a look at this process then, now that we've superimposed capital letters to represent the automobile process rather than just some generic process. You've got a desired speed. You're looking at a speedometer. So in here you've roughly got your, this is where you've got your head, your brain, your central nervous system, because you're dealing with your body is basically part of this control loop because you have a desired speed, and then you actually are the one that is looking at the speedometer, getting that value. So you internally measure the difference between the desired speed and the pedometer, and depending on that difference, which is a very complicated psychological function when you get down to it, you're going to get an error. And based upon the value of that error, that's what drives the pedal. Either you're going to let up on the pedal or press down further on the pedal. That pressing down on the pedal is very easy for you, but of course needs to be amplified into some sort of movement if we're going to move the car anywhere. So that's where the engine or the power amplifier comes into play. The input for the car example, the stochastic input might be the gradient on the road. I'll just put gradient. That's a kind of random input that may well change the performance of the engine and thus the entire feedback process. And lastly, you've got the car. That's the thing being controlled, is the entire car. And the car would have to be modeled likely as a large mass, something that is over 1 ton in weight and is quite something to try and coordinate and control. Now this pattern that we showed earlier, whose elements are still here, control, actuator, error, reference signal, this can be applied to a huge variety of different artificial systems, generally where the human is connected to an engineered system. I mean, another example, in addition to this automobile one we went over, is the shower. A very common example of automatic control or manual control in this case. So you've got a desired temperature with a shower. You've got some kind of transducer. This would be your skin that measures what? The temperature of the water. And you've got the process, and the process is the process of diverting the amount of hot water versus cold water. So you've got a tap that you've got to control. And then the taps would serve the same role as the pedal. They would serve to divert flow or increase the amount of the flow. And so again, this template is exactly the same for taking a shower, essentially, as it is for driving and controlling a car. And you can substitute many other types of systems in for this. So it turns out to be a very valuable type of model. But it is a functional model in that you do have directed flow, and you do have these blocks or functions that take the flow and operate upon it. Now in this example, we're not going over what specific mathematical functions are used to capture and accurately represent the transducer or the thing being controlled or the amplification. But in practice, you would have to have mathematical functions associated with each one of these blocks, and then you would be able to go through and do a simulation of it. Our next type of functional model is a little bit different. It's a queuing model. And in the queuing model, you've got discrete flow. You've got discrete items that are flowing through the network. So the blocks can contain queues and facilities or resources. A facility can contain one or more servers. So already we can tell with queuing models that it's got its own verbiage and vocabulary. A service can be first in, first out, or there could be a priority scheme associated with this. And you may implement blocking, which halts the flow of tokens and data through the network. So queuing models are very good at representing the flow of discrete items, anywhere from if you're going to, say, model the internet or a local area network or any kind of communications or information-based network, you would use a queuing model, as opposed to the kinds of models that we've just been talking about, a control model, where you don't have a set of continuous data, rather you have physically based signals that occur in a continuum over time with respect to time, and those are the things that are entering and exiting the functional blocks. As an example of a queuing model, let's use a manufacturing floor. And what we're going to do is we're going to have a generator of parts. And so we'll put an X right here and just say gen for generator it's going to generate parts that flow into an accumulator. And we're going to put ACC for the accumulator. The accumulator then will accumulate parts as they're generated and feed them one by one to the lathe, which will operate upon these parts and pass them to an inspector, a human inspector. So we can look at this as a queuing model. Let's draw some extra pictures right here. Queuing models have different sorts of presentations, but one common two-dimensional presentation for queuing model is to show the queue and then the entities or jobs or tasks, the individual discrete items being queued, as something like this. This is by no means ubiquitous, but is one way to show this. And then you have perhaps a facility with a certain number of servers. Like this has got 3 servers, and each server is represented by a circle. So this is a facility. These things in here are servers. These are tokens or entities, the things that are being queued. And this is the queuing structure right here. So what ends up happening visibly is that the tokens come in here, get queued up for service, and will get directed to a facility that may or may not have one or more servers. And if it's got more servers, then chances are that they will be served quickly without having to cause undue amount of queuing on the tokens that are waiting to be served. You've basically got an input into this and an output from it. And the simplest form is where you just simply have one server. So you have the structure like this. Something coming in, something going out, entities that are waiting to be served. So this represents kind of just some diagrammatic language that we can use in our example for the manufacturing floor. So what we're going to do then is the accumulator, we're going to say, can basically handle any size queue. In practice, this is not going to be the case, but the accumulator, for all intents and purposes, may be able to handle as many items as you can give it. It's a big accumulator. Okay, so we would just say that the size then is equal to infinity. Now the lathe is a little bit different, okay? The lathe, again, is we've got a queue and a server, but the size of the queue, we're going to say, is going to be 0 for the lathe. So what we're going to say is that the lathe is in fact modeled by a server, and yet it can't handle, there's no room for it to queue any entities, or in this case objects, parts that are flowing through the system. The lathe can simply take a part and operate upon it, serve it, and then pass it on to the human inspector. And we'll say the human inspector has enough capability to be able to queue up to 3 parts. So we'll say a size of 3. So in looking back on this, if we didn't have any worry about the size of queues, then we would have parts flowing from left to right through this system. Things would get queued up basically depending on the inter-arrival time of the parts with respect to the service time it takes for each of these individual resources. So queuing is, a way to think about it from a functional block model perspective is, queuing models are functional block models. The functions are fairly complex because the functions don't simply add a couple of numbers or a couple of signals together or multiply them or integrate them. Instead, they do integrate them, but in a more intelligent, artificial fashion. They queue up the signals or the entities that are identified and marked by the signals that enter this block, and they queue up that stuff, which has to be stored somewhere for processing, so that we know that when they're served, that they end up going out of this block. Now, often in practice, inter-arrival times, or in this case the time it takes between parts to be generated, might be dictated by a stochastic function or probability density function. This is also true of the probability density function for the server. These servers will likely have an amount of service time dictated by data that are captured on site where the physical process of the manufacturing floor is, where you have the manufacturing floor, and that data, when captured in bulk, produces a probability density function which approximates or models the amount of service time that is required by each of these three resources, the accumulator, lathe, and inspector. So in practice, that's what you have, is you've got a lot of statistics that is required in order to produce the density functions or the models for input for this system. Now, one thing to note, though, with something like this, where you have a lathe, which, even though I've drawn a few lines in here, which I probably shouldn't, maybe I should erase these because we have a size of 0, we note that this can't handle anything queued. It simply has a server, and that's it. So because of that, the simulation mechanism, if we're going to build a simulator for this, if we wanted to build an actual simulation system for this, we'd have to make sure that the lathe communicated back to the accumulator saying, hey, don't send me anything more. I can only handle one part at a time. And likewise, the inspector would have to do something similar. He had to keep track of how many parts are in his queue, and if he had 3 things in the queue, he'd have to send a message back to the lathe saying don't send anything, which in turn would have to send a message back to the accumulator, which in turn might send a message back to the generator. This situation is called blocking. The ability of one resource to send messages back to the prior resource in order to block the entity from moving forward.